Liliana from University of Lausanne in Switzerland, and I will continue with convergent sales, probably a bit less funny than the previous one, but let's see. Okay, so here I present you a series of plant species from the wild mountain in Arizona, and you may agree with me that they look quite alike, but despite that they are phylogenetically distant. So these similarities in morphology, especially in color and size and shape, may be the result of functional convergence and ecological interactions of these species. And in the long term, it's the product probably of the similar selective pressures that they are subjected to. So if we recognize that they are very similar morphos, we also wonder if there are similar genetic mechanisms underlying these morphologies. But what are these mechanisms? Recent research in floral zygomorphy in neotropical lineages that they try to identify the repeated evolution of zygomorphic flowers in neotropical lineages elucidated that apparently there is a lot of loss of function in specific genes, but also expression changes interacting in this repeated evolution. So we see from here that the mechanisms can be quite varied, and the levels of genetic control can be either selected on the specific genes at the sequence level or on the expression of those genes. So here I wonder what is the contribution of these different genetic levels: genetic expression, substitution rates, and selection signatures. To investigate this, I use a system that is Gesneriaceae family and the evolution of similar floral morphologies. This family is very interesting because it has a lot of floral differentiation that is associated with different pollinator types. And from previous analysis at the phylogenetic level, we have identified that there are common shifts between pollinator types. They are highly common between insect-type flowers, which corresponds to the blue branches here, and hummingbird-pollinated flowers that are the red branches. So once we have this interesting system, my experiment consisted into selecting 3 pairs of species, each one underlying one pollination shift, and therefore changes in floral morphology. To summarize the methods, I'm happy to discuss in details. We sequenced the de novo transcriptomics sample for 6 species at different developmental stages. We infer the orthologous group chairs between these species. We perform models of differential gene expression, the estimation of substitution rates for these genes, and the estimation of selection signatures. So their results I'm going to present in the following way. As we want to compare between different levels of genetic mechanisms, I have in this axis, in the y-axis, the different responses of possible molecular mechanisms, and in the y-axis, the contribution or the total genes that presented these signatures. We see here that expression level is almost 4% of the total amount of genes that we have shared between these species, and they are mainly conserved response or concerted response in the bee-pollinated species. We have here, over developmental time, we increase the number of concerted responses, and the number is lower for the hummingbird-pollinated ones. If we move to the next step, rapid divergence, we find quite the opposite pattern, that hummingbirds are the ones that are evolving faster, and this is correlated also with the signatures of selection, in which we find purifying selection more common in bees than in hummingbird-pollinated flowers, and we find more positively selected or divergent proteins in hummingbirds. Just a take-home message, so we have different levels of response or concerted responses at the genetic level. There are more concerted expression in bee-pollinated flowers, and sequence variation is higher in hummingbird-pollinated, and from this point we can access to candidate genes for further comparisons or additional research in how correlated they are or if there are structural changes. I would like to thank my collaborators